we talked about improper integrals. Now we're going to go to section 8.1 and talk about arc length. So this is where we're going to try and, well, we're not going to try, we're going to succeed to find the length of part of a graph above some interval. So if we have an interval a, b, and some specific function f, then we want to know what the length of this graph is, right? The one-dimensional length of the curve created by this graph. And we have a formula for this, which wasn't hard. It just came from pictures, just from doing Pythagoras' theorem. And it's this, right? So this 1 plus f prime squared was because when we looked on a small scale, then we were comparing this thing, how much we're moving, start again. We're comparing this thing, how much we're moving across, to how much we're moving up, which turned out to be related to the slope, of course. So if we square this thing and take the square root, that's where we get this kind of structure from. So this is a very natural formula. And with this formula, we can simply calculate this arc length of arbitrary graphs, right? So let's do an example of this. So find the length of y squared equals x from 0, 0 to 1, 1. Okay. So let's draw a picture to see what we're doing. Oops, it's not like this. So it's y squared is equal to x, right? So we've already given this as a function. Okay, so this is what this curve looks like, right? Not bending quite as fast. This is what this curve looks like. This is 1. And this is 1. So it's already been presented to us as a curve from the y-axis, right? So x of y equals... We could write it as a curve from the x-axis, but it's easier to think about it like this, right? Because it's already in this form. So this is what it looks like. And we're trying to find the curve of this guy here. Yeah. And we are just going to use the formula. That's all we have to do, right? So the formula tells us that if we integrate from 0 to 1 of this expression, that is the arc length, right? So the square root of 1 plus x prime of y squared dy. That's just applying the formula. Yeah. Yeah. And then this is something this is going to be a 4. We can simplify a little bit by pull out the 4, and then we're going to have to integral from 0 to 1 of the square root 1 plus 4 plus y squared dy like this. And then this is something where to go forward, we're going to have to do a trig substitution, right? This is exactly the kind of format of a trig substitution. So can you see what is going to be the reasonable trig substitution to use here? So trig substitutions, we have our two identities. And given these two identities, what's the reasonable substitution to do here? So if we see this 1 plus tan squared, we have some constant plus y squared, so it's natural to try and replace the y by tan. So we let y of equal tan of theta, and if we do this, dy by d theta equals sec squared of theta, So we're going to have to pay for this by having this sec squared of theta d theta, right? So I'm going to put the limits in a second. First, I'm just going to rewrite this thing. But I want it to be a half because I want to pick up this quarter here. So then I have a half here. So then I have a half here, right? So then y squared equals 1 over 4 tan squared. And then in this identity here, we have that 1 over 4 plus y squared is 1 over 4 of 1 plus tan squared. Which is 1 over 4 sec squared of theta, right? So this thing gets replaced to be the square root of 1 over 4 sec squared of theta, and then this dy becomes a half of sec squared of theta. Okay, now we have to think about the limits. So these are the limits from 0 to 1 when we are in terms of y, right? And y is given by this thing. So that means that 2y equals tan of theta, and therefore theta equals arctan of 2y. Yeah? So when we stick in theta y equals 0, then arctan of 0 is 0, right? The graph of arctan we know well, right? And when we stick in y equals 2, then we're going to have arctan of 2. Yeah? So these limits now become 0, and let's call alpha arctan of 2 because it's going to be long to write. So let's call alpha where alpha equals arctan of 2, like this. Yeah? Everybody happy with this so far? Yeah? And then we just have clean up. So there's a half goes over here, and we're going to get a half from this. So we have a half, and we're going to have 0 to alpha, and then we're going to have, so this is sec squared square rooted, so now it just becomes sec to the power 1, so we have sec to the power 3 of theta d theta, like this. Yeah? And now we have just an ordinary trig integral, yeah? Which we have to break up this sec squared into 1 plus tan squared using this, and then we can integrate one of these by substitution. The other one is a standard integral, the antiderivative of sec squared. Sorry, the antiderivative of sec. And yeah, this I am not going to complete. So then it's just doing that kind of stuff. The key thing, however, is just to do the formula. Get the formula right, put it inside the formula, and then you have an integral of some kind where you apply your integration methods. And if this is a free response, that's what they really want, is that you get the formula right, you do this in a meaningful way. If you have this in the free response, it might be something that requires a substitution, it's kind of difficult-ish integral. But if it's not going to be as hard as this. It's going to be a fairly easy question no matter what. Okay, so the next topic is surface of revolutions. So this is 8.2, area of surface of revolution. And in a way, it's a similar topic in that we just have a formula we have to apply, but we have to get the formula. We have to know the formula and apply it correctly. So this is where we have some kind of a graph of a function, f, and we are taking this graph and we are rotating it around an axis. So in the simplest case, we're going to rotate it around the x-axis. So I draw this kind of symbol, this kind of arrow to indicate the axis that we're rotating it around. And if we do this, we get a kind of two-dimensional shape, right? Like this. Right? So we got a kind of two-dimensional shape, cylindrical shape, and that thing has this two-dimensional area, and we want to calculate it, right? So this tube is an example of a surface of revolution, right? Because if I just had a constant function and I rotated it around the axis, I'd exactly create a tube, right? So we are going to find out the two-dimensional area of this thing, right? And we did it in exactly the way we found all these formulas. We just cut things up into little tiny pieces. And then we looked at a little tiny piece like this, you know? And then if we looked at a little tiny piece, then the issue was, so this is not a good picture, the issue was, what is this length right here? Because if we cut out this piece, we see a kind of a strip, right? And the strip is going to form some kind of a circular shape, and the radius of the circle is given by this length, but the thickness of the strip is given by this length, right? So those are the relevant quantities. So this is, if this here is x, then this will be f of x. And then this thickness here obviously depends on the slope of the function, in other words, the derivative of the function at this point right here. And with a very similar reasoning, just exactly the same pictures actually, as when we get the surface area, we can find out what the thickness of this strip is. And it is basically given by the square root of 1 plus f prime of x squared times delta of x, where delta is this thing over here. Okay, so then we have we're going to have the circumference of the strip, because we know that the radius of the circle creating it is f of x, so it's going to be 2 pi f of x. And we're also going to have the thickness of the strip, because it's going to be given by this thing. Yeah? So this strip will have surface area given by 2 pi f of x, square root of 1 plus f prime of x squared times delta of x, right? And then we just add up all these strips and we end up with an integral, and it's the following. So surface area, I'm going to abbreviate to SA, is the integral from a to b of 2 pi f of x, the square root of 1 plus f prime of x squared dx. Once you have the formula, once you're comfortable with the formula, then this is an easy subject. And I claim that the formula follows straightforwardly from these kind of pictures. So if you feel any discomfort or any lack of confidence about this formula, the best thing to do is just to go from this picture and work it out for yourself, which I promise you can all do. Failing that, just go back and watch the video, watch the explanation. This is a natural and easy formula to believe. Once we have it, then we just use it to calculate. So let's do an example. Given y of x, which is given by this thing, for x between -1 and 1, find the surface area of revolution when rotated around the x-axis. Okay, as always, we're going to start with a picture. All right, so what does this look like? Where do you recognize this? So when you see x goes to the square root of 4 minus x squared, what's that? No. Yeah, it's a part of a circle. Because if we do this, y of x squared plus x squared with this thing here, what we have 4, whoops, put the equal sign over here. This is equal to 4 minus x squared plus x squared, which is equal to 4, right? So it says that the x and y coordinates satisfy this equation, y squared plus x squared equals 4, which is exactly saying the distance of yx from 0 is 2, right? So this is part of a circle of radius 2 around the origin, yeah? So at this point, I'm hoping that this thing is a familiar thing. I mean, this is a useful thing to know because there are problems where if you recognize it as part of a circle, then you're going to have a very good idea what the answer is anyway, right? So if we are asking you to integrate this from 2 to 2, right? You could fight with this with some trig substitutions, or you could just recognize it's part of a circle. It's actually half the circle, right? If we integrate from -2 to 2. And therefore, you just know the area by taking the area of the circle divided by 2. So it's really useful to be familiar with this, to see that this is part of a circle. Yeah? This is the upper half of a circle, this graph. And what we're actually integrating is it from -1 to 1. So it's this part right here. Yeah, and we're rotating this thing around the y-axis. So it's like a kind of soccer ball, which I happen to have with me. So it's like part of a soccer ball, right? But we just consider the surface area of the soccer ball over some slice through the soccer ball. Yeah, that's what we're doing here. Yeah, and that's potentially quite a reasonable practical problem. You could be working in a soccer ball factory, and you could have the soccer ball have this strip be a different kind of plastic or different color plastic than the other part of it. So you want to know what the area of this is, so you know how much plastic of that kind, of that color to actually order, right? So we have the power to figure this out because we have this formula, this exact formula that tells us what it's going to be. Yeah? So all we have to do is plug it in the formula. So we're going to integrate from -1 to 1 to pi times this thing. Okay, this is the perimeter of the strip, and then 1 plus, and then we take the derivative of this thing. Let's put the derivative over here. So y prime of x is 1 over 2, 4 minus x squared, minus 1 over 2, and then we differentiate what's in the inside. It's 2x, like this thing. So that cleans up to be minus x over square root of 4 minus x squared, like this. No? So we have this thing and we're going to square it. So we're going to have x over 4 minus x squared dx. And that thing is our expression for the surface area of this thing, of this surface of revolution. That's one of the harder parts, is just to set up the integral correctly. Are you all with me that this is the right thing? Thumbs up if yes, thumbs down if no. Yeah, it should. So that was an unintentional test question. All right. Everybody happy? Everybody with me? Yeah? Cool. All right. And then we just want to do some algebra to make this as simple as possible, right? So what's the natural thing to do? We want to make the denominator the same, right? Let's pull out the 2 pi. I mean, at this point, it's just doing an integral. It's just into this integration methods techniques, right? So, and then we're going to have 4 minus x squared plus x squared, which is pretty convenient. Right? The x squareds are going to cancel. And then we're going to be able to take out this. We're going to have this. It's just going to be square root of 4 on the top, which is just 2, underneath the square root of 4 minus x squared, right? And this denominator will cancel with this thing. So this entire expression really simplifies nicely, because all we're going to have here is just 2. Yeah? Cool. So then we're integrating this 2 over the range from -1 to 1, which is 2, so it's going to be 4. So it's going to be 4 times this, which will just be 8 pi. Like this. Yeah. And that's the answer. That's exactly That's exactly the surface area. Everybody good with this? Yeah? So setting up the integral is the key thing, and then it's just doing an integration. All right, cool. Let's keep going. So the next topic is sequences. Okay, erase it. I have to erase. Okay, sequences. So what's a sequence? It's just a collection of numbers which we put in order, right? So we can have A1, A2, A3, A4, and so on, right? It's just an infinite collection of numbers that we can label with integers 1, 2, 3, and so on. Yeah? That's all it is. And we visualize this by simply putting it on the axis above whatever integers we have. So if A1 is whatever it's here, then that's what we'll put a dot that represents A1. If A2 is negative, then we do this. Maybe A3 is down here. Maybe A4 is here, right? So we can just visualize this as a collection of dots like this. And that's what you're going to have to do. That's what this thing means. Yeah. So once we have a sequence, then we can start to discuss things like its limit and whether or not it's increasing or decreasing. Let's start with a simple example. So let's do this. An equals n over n squared plus 1. What does that sequence look like? Well, as n increases, right, the bottom is increasing faster than the top. Right, so it kind of looks like the sequence is decreasing as n goes towards infinity. You would expect this to tend closer and closer to 0. Yeah? Yeah? But we have a way to be precise about this. We have a way to say that in a clear, unambiguous way, what we mean by that. And what we mean by that is that whatever strip we put around 0 like this, we can guarantee that these guys are within that strip so long as we are far enough to the right. Yeah? So after some point, whatever they might be doing initially, at some point, it's going to be inside this strip around 0. In fact, this case is monotonic, so it's definitely not doing that, but something like that. Yeah? Which is cool because that means we can guarantee that what we want to happen is going to happen in the limit as n goes towards infinity. That's the meaning of limit. That's why we can do these things that we can't do. Otherwise, we could not have developed this formula I just talked about unless we had this concept of limit, because we needed this limit to pass from the finite sum when we cut up these pieces into little strips to the infinite sum when we took the limit as n goes to infinity, right? This concept of limit is not just fussiness. It's not just being over interested in precision. You simply can't have a meaning for things unless you have this concept of limit, right? And actually, the concept of limit is in many ways simpler when you talk about sequences than when you talk about functions. These are simpler objects than functions. All right, so that's a sequence, right? And this sequence looks like it's decreasing, but we want to check it's going to be decreasing. So is this decreasing? Well, we could mess around, right? So decreasing means that each term is less than the one before, right? So we could do some algebra just messing around with this, but there's a better way because we have the tools of calculus. So what's a better way to show that this is decreasing? Exactly. We create a function recovering the sequence. Keep going. So this is the picture, and then take the derivative. So if we have a function recovering the sequence, which is what I'm drawing now, then if the function is decreasing, then for sure the sequence is decreasing because it lives on the function, right? And that's an incredibly powerful thing to be able to do, right? So that's something that we do a lot. To understand something like a sequence, we'll say, okay, what function is going to create this sequence? And let's talk about the function instead, because the function is something we can apply the tools of calculus to. So let f of n be equal to an. That, in the language of maths, is just this picture that I've drawn, right? Because f of 1 equals a1, f of 2 equals a2, f of 3 equals a3, and so on, right? What function is going to do that for us? Someone hasn't spoken yet. What function will do that for us? F of x equals what? Come on. Perfect. That thing exactly does what we want. We stick in n into this, we get exactly an. Yeah? And then now we can just differentiate. Just have to apply the quotient rule, so everything over the bottom guy is squared. Differentiate the top and leave the bottom alone. So we're just going to have x squared plus 1 minus, leave the top alone, differentiate the bottom, right? And we're going to have minus x squared plus 1 over x squared plus 1 squared, which is less than 0 for x bigger than 1. So from any x bigger than 1, this thing is definitely decreasing, so it's a decreasing sequence. Yeah? And that's a much easier way. I mean, you can also do this by playing with the algebra, but that's a much easier way than that, right? So keep this trick in mind. This is a basic trick. We have to we get a lot of value out of applying. All right. I'm gonna just skip to the series now. So let's talk about series. What is series? So given a1, a2, and so on. So given some pre-chosen sequence, we might want to add it up. We might want to add up this infinite collection of terms. But we have to think about what this means, because we can't just sit there and add something infinitely many times, right? Life is finite, the universe is finite. This has no actual meaning by itself, right? So what this means is that we're going to take the limit as capital N goes to infinity of the sum, well, actually, I'm going to use the partial sum notation, of Sn, where Sn is the sum from little n equals 1 to capital N of, let me use k, of ak. Well, again, this has no meaning unless we define it via a limit, and we can't do it without a limit. So this whole thing just is meaningless unless we use this concept of a limit. Literally cannot proceed with mathematics without limits, right? So why is this the valid notion? This is the valid notion because there's no other way you can possibly make sense of this, right? If you are writing a computer program trying to give some meaning to an infinite sum, this is exactly what you would do. You would just sum the thing to as big a term as you possibly can, right? And imagine you did this on your laptop, on your Chromebook, then maybe the largest n you could take would be 6 million, right? But then you went to your desktop and then you could take this n to be 45 million. And then maybe you went to the university's very best workstation and you could do it to 100 million, right? Or 200 million. There's only way that you get a meaningful thing in all those cases is if as the number n goes to infinity, the answer converges closer and closer to some particular thing, right? If, as you did your computer program on all these different machines, you got completely different answers, then you have no meaning to that sum. That sum is of no use, right? There's no point considering it. It has no meaning. Yeah? So the constant of limit is the natural and the only way to define this infinite sum. Yeah? It's the only way to define this infinite sum. And with this concept, we can actually consider this infinite sum, and we have this more general way of doing addition, right? And it's a very useful thing, right? So, key example. If we consider this thing, this thing has literally no meaning. It's not anything. It just has no meaning. It is not anything that we can give any meaning to, because what is this then? This is the sum as n goes to infinity of these partial sums, and the partial sum just depends on whether or not we have n is even or odd, right? So if n is odd, then we're going to get a negative number, and if n is even, we're going to get 0, right? So this thing will just flip between 0 and -1 forever. Yeah? This thing has no meaning. This thing has no meaning. So this is meaningless. Yeah? So we need this limit to actually exist in order for us to make sense of an infinite sum. Yeah. All right. So there are a couple of infinite sums where we can actually calculate the answer, and they are very good examples. The simplest example is the geometric series. Whose simplest formulation is like this. Note that I'm starting from k equals 0, and that's important. Okay. So if we let Sn be the sum from k equals 0 to capital N of r to the k, then a little bit of algebra shows that if we multiply it by r, then we get the sum from k equals 0 to n of r to the k plus 1, which is the same as the sum from k equals 1 to capital N plus 1 of r to the k plus 1. So then we can take this thing away from Sn, so we're going to have 1 minus r Sn. It's the same as taking Sn and then subtracting r times Sn. And then what do we get when we take this thing and subtract this thing? Well, the 1 will survive from this because it goes 1r squared, right? And this thing starts at r, goes r squared, blah, 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 right? So the 1 will survive because it won't get killed by this thing, yeah? But that's the only thing from this expression that will survive. And what we'll have left on the right-hand side of this thing will be minus this r to the n plus 1. So we're going to have 1 minus r to the capital N plus 1. Yeah? So then we divide through. So I'm doing this fast. I'm aware. And we get this. Yeah? And then we see that if we let n goes to infinity, if r has got absolute value less than 1, then this thing here will go down to 0, and therefore we get something meaningful. We get a meaningful limit out of this as n goes to infinity, so long as r is less than 1, right? So if then we can make sense of this. This limit does exist, and this is 1 over 1 minus r. And this is a basic formula that is really useful because we use this over and over again. Right? We use this when we start discussing early power series or simple power series. We turn things into things like 1 over 1 minus x because we have this thing. So this is an absolutely key formula. It's worth your while doing this little algebraic step. It's one line just to reassure yourself you know why that this formula is this form. Yeah? Cool. And once we have the formula of this form, then we can get any kind of version of it. So the most general version is we take the sum from k equals m to infinity. Maybe we have a constant in front, r to the k. If we just factor a and r to the m from this, then we're going to have a r to the m, the sum k equals 0 to infinity, r to the k. And then it's exactly the formula we know. Like this, yeah? So we can explicitly calculate any power series of this kind. It's called the geometric series, yeah? And this will only converge if absolute value of r is less than 1. If absolute value of r is bigger than 1, then this term in the box here blows up, right? So then it clearly can't converge. This thing's going either to infinity if r is positive, or it's oscillating between positive and negative infinity, more or close and close to positive and negative infinity if r is negative, right? So it has no hope if absolute value of r is bigger than 1. And it's also not hard to see that if absolute value of r is equal to 1, this thing also makes no sense, right? The limit of this thing won't exist. Okay, so that is one of the simplest examples we have. It's the geometric series. Everybody happy with this before I erase? Yeah? Thumbs up if yes, thumbs down if no. Actually, maybe I want to give you an example of a geometric series before I do that. Let me just give you an example of using the formula. Okay, what about this? Suppose we have 5 minus 10 over 3 plus 20 over 9 minus 40 over 27 plus, and then so on and so on and so on. Okay, so a good hint is whenever you see a question like find the exact sum of this, then it's got to either be a geometric series or telescoping series. And this thing, as what later can see, is not a telescoping series. It has to be geometric. So we have to look for a geometric structure out of this. So a smart policy is to try and divide by some common denominator to make this thing simpler. And the natural one is 5 in this case. So we do 5. Then we're going to have minus 2 over 3 plus 4 over 9 minus 8 over 27 plus dot dot dot, right? And now we see a geometric series structure emerging because this is minus 2 over 3 to the 0. This is minus 2 over 3 to the 2. This is minus 2 over 3 to the 3, and so on. Yeah? So this is the same as 5 times the sum from k equals 0 to infinity of minus 2 over 3 to the power k. And once we know this, then we just stick it into the formula, right? So this 5 should be better written. So putting this into the formula, we have that this is 5, 1 over 1 minus r. In this case, r is minus 2 over 3, so it's 1 plus 2 over 3. So I'm going to write this as 5 of 1 over 3 over 3, so that becomes 5 over 3. And then these 5 cancel, and this is just 3. Yeah? So with the formula, it's kind of easy to find out any geometric series. Okay, telescoping series. So, telescoping series, very different nature. They go to 0 much more slowly, generally speaking. And here is a classic example. The sum from n equals 1 to infinity, 1 over n to the n plus 1. They're called telescoping because when we consider the partial sums, many of these terms will just flatten out. So, solution. So this thing is the sum. Well, the sum is the limit as capital N goes to infinity of the sum from k equals 1 to capital N of the partial sums, right? N over n plus 1. So we need to understand these partial sums here in order to do this, right? So this is the thing that we'd like to understand. And if we look at this thing, this 1 over n plus 1, then we should be able to write this as a over n plus b over n plus 1 for the right choice of a and b, just from the same kind of stuff as we learned in partial fractions. So to figure this out, let's make a common denominator. And the only way this is equal to this for every n is if the numerator agrees. So we have a plus b of n plus a is just equal to 1 for all n. And this implies that a plus b has to equal 0. There's no other way that this could be true, right? Because if a plus b was not equal to 0, then this thing goes off to infinity as we let n go to infinity. So it implies a plus b is 0, and it also implies that a has to equal to 1. Therefore, b is minus 1. So we have that this thing can be decomposed like this. Is equal to 1 over n. 1 over n minus 1 over n plus 1, like this. And that's what's going to happen in all telescoping series. We're going to have something like some term minus the guy that comes after it. Yeah? Because once we consider this partial sum in this box, So the stuff in the red box is now the sum from, we're switching from n into k. K equals 1 to capital N of this stuff. 1 over k minus 1 over k plus 1, which you can break up as the sum from k equals 1 to capital N of 1 over k minus the sum from k equals 1 to capital N 1 over k plus 1, right? And you see what's going to happen. This thing is going to have a massive amount of cancellations, so we can rewrite this as the sum from k equals 1 to infinity, 1 over k. And let's take the sum from k equals 2 to n plus 1 for this thing. So we can write this as sum k equals 2 to capital N plus 1, 1 over k. And you see that there's this huge massacre. Many of these terms will die. And the only survivors will be just when we have k equals 1 from this thing, and then minus 1 over n plus 1 from this thing. Yeah? If you're in any doubt, just write this out. The first term, the second term, blah, 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 up to the nth term, and then same for this thing. And you'll see that everything that's not the first term in this thing will get wiped out by something on this, right? And there'll be one guy left, which is the nth plus 1 term. So that is how we do this. I've overrun. Of course, leave any time you want. I want to get a little bit further. And what happens with this? Well, this thing is our partial sum, right? So we take the limit as capital N goes to infinity of the stuff in the red box. We are just going to get 1 because this thing goes to 0. So we can explicitly calculate this sum, right? So this infinite sum is just equal to 1. It's just equal to 1. Yeah? Cool. And that is the nature of any other telescoping series. It's going to be something where after you do some kind of partial fraction type decomposition of the products on the bottom, you're going to get something minus the guy after it, so that when we consider the partial sums, there's this huge wiping out of terms, and then you'll be able to explicitly see what the limit of the partial sums is, right? So those guys and geometric series are up to this point the only explicit things we can calculate with series, the only explicit answers we can actually put in, right? Everything else is about, does the series converge and how well can we approximate it? Yeah? That's the rest of these multiple sections is about series, but we're asking, do the series converge? And then if it does converge, how well can we approximate the answer? Yeah? So this is a big kind of conceptual shift for many of you. Up to this point, for most of you, maths has been about finding the exact answer to stuff. Now we can't do that anymore. But what we can do is something just as good. We can find the answer, and we can find the approximate answer, and we can know how close the approximate answer is to the actual answer, even though we don't know what the actual answer is. Yeah? It's kind of weird and conceptually surprising that we can't find the actual answer, but we can find the approximate answer to arbitrary precision without knowing what the answer is. But that's what we can do with the power of this stuff. All right, let's do a final topic just quickly. Let's talk about the first and most basic thing which we can do to determine if a series converges or not, and that's called the integral test. I think that's 8.2. All right, so this is only for positive terms. So if an are positive, so most of the time we're going to be talking about series of positive terms, but not all the time. Not all the time. And we have some theorems that only work when we have positive terms, and this is one of them. Okay, but if we have a series of positive terms, it's very convenient to draw it as a collection of blocks. So if A1 is our first term, let's draw a block of height A1 between 0 and 1. Let's draw a block of height A2 between 1 and 2, right? A1, A2, and so on. They don't have to be decreasing as I'm doing it, but that's just what I'm going to do. Yeah? And then if we ask ourselves, does the series converge? Well, the series converges is exactly saying that the area underneath all of these blocks is finite as we take the sum of all of them from 1 up to infinity, which is the same as saying that the area underneath the graph created by this thing is finite all the way from 0 to infinity. Yeah? Cool. So one of the natural things we can do is simply create a function that looks an awful lot like this, and then ask ourselves, what about the area underneath the graph of the function that looks an awful lot like this? And it turns out that these things are entirely connected. So if f is positive, continuous, and decreasing, and f of n equals an, then the area of the graph of this function being finite and with the integral converging is entirely equivalent to the series converging. So it goes up here to here. So then series converges I should perhaps say explicitly what the series is. The series, given by the sum from n equals 1 to infinity, an converges if and only if the integral, and we can start from any number. Let's start from number capital A to infinity, f of x dx converges. Because this stuff is about what happens as we let things go to infinity, so we don't actually care where we start from, right? And this is an easy theorem because it just follows from the picture, right? So what does this mean? This means that our function is doing this. It's going through like this. So we can just see that if the area underneath the graph of the function is finite, then for sure the area of all these blocks is finite. Yeah? You can just see it just from this picture. And the only thing that is required to see the full statement, because what we have from there is one implication that the finiteness of this implies the finiteness of this, so we see this direction from that statement, is just noticing that if we create a new function, g of x, which is equal to f of x plus 1, right? So g of 1 equals f of 2, g of 2 equals f of 3, and so on. Then what is the function g going to look like? It's going to look like this. Right? So g of 1 equals f of 2, so it's here. Right? G of 2 equals f of 3, so it's here. And this function g is now underneath our blocks. Right? So this is our function g. Yeah? So if the area underneath all of our blocks is finite, then the integral of the function g has to be finite, because it's underneath all the blocks. Yeah? But then that means if we integrate from whatever, say 1 to infinity g of x, and we know it's finite, that's almost exactly the same thing as integrating f, because all we've done is shift f forward by 1. Right? It's almost exactly the same thing. So that's the integral from 1 to infinity of f of x plus 1. And then we can just do a change of variables. Let's just start from 2. We can just do a change of variables, and that's just equal to the integral of the function from 1 to infinity f of x dx. Just let u be x plus 1. Yeah? So this thing has a reverse implication, and if the area underneath the blocks is finite, then the integral is also finite. Yeah? So we can entirely replace the question of whether or not this series of positive terms converges with the question of whether or not this improper integral of type 1 converges, which is something we've already studied, something we already know how to do. Yeah? Cool. So this is the integral test, and it's a very useful test, but it's also a heavy weapon because it means explicitly calculating an integral and checking that our function satisfies our conditions. We need to check that it's positive, decreasing, positive, continuous, but most importantly, decreasing, which often means taking the derivative, right? So we can use this. We can use this and answer the question in lots of cases, but we don't want to use this unless we have to, because it's calculation. It's harder work than the other techniques we're going to talk about on Wednesday, right? So this is one of our first techniques. It's very simple to understand why it works, but we don't use it unless we absolutely have to. All right, that's enough for today. So when I have office hours, stick around if you have any other questions. Otherwise, I'll see you all on Wednesday. Have a great day, people.